The numbers arrived on a Tuesday morning in March 1963. At the Palomar Observatory in California, astronomer Maarten Schmidt sat at his desk, examining spectroscopic data from an object catalogued as 3C273. The source appeared as nothing more than a faint, bluish point of light in photographs, easily mistaken for an ordinary star. But the radio telescopes told a different story. This star-like object was one of the most powerful radio sources in the sky. Schmidt studied the spectrum, searching for the familiar patterns of absorption and emission lines that would reveal the object's composition. The lines were there, but they made no sense. They didn't match any known pattern. He spent hours trying different interpretations, growing increasingly frustrated. The spectral lines appeared in positions that corresponded to no known element, no familiar atomic transition. He cross-referenced tables of spectral lines, considered exotic molecules, wondered if instrumental errors might explain the bizarre pattern. Then, almost by accident, he recognized the pattern. It was hydrogen's Balmer series, the same lines that appear in the spectrum of our Sun and countless other stars. The signature was unmistakable once he saw it. The H-alpha line at 656 nanometers, the H-beta line at 486 nanometers, the entire familiar sequence. Except these lines weren't where they should be. They were shifted dramatically toward the red end of the spectrum, displaced by 16% of their normal wavelength. Each line had been stretched, moved toward longer wavelengths, in a way that spoke of tremendous velocity. Schmidt felt his understanding of the cosmos shift. That redshift meant this object was racing away from Earth at 47,000 kilometers per second, roughly 16% the speed of light. If Hubble's law held true, if this redshift resulted from the expansion of space itself, then 3C273 lay more than 2 billion light-years away. To be visible at such an immense distance while appearing star-like in optical telescopes, it would have to be radiating with the power of 100 billion stars. More luminous than an entire galaxy, yet concentrated in a region small enough to appear point-like even through the world's most powerful telescopes. The implications cascaded through his mind. At that distance, the object's apparent brightness of 13th magnitude meant its absolute magnitude must be around -26, brighter than anything in the known universe except for brief supernova explosions. But supernovae fade within weeks or months. This object had been observed for years at relatively constant brightness. It was sustaining an energy output that seemed physically impossible. Schmidt knew what he was seeing shouldn't exist. No known mechanism could explain such staggering luminosity from such a compact source. The energy output defied everything astronomers understood about how objects in the universe could shine. Stars generated energy through nuclear fusion, but even if you packed 1 trillion stars into a small region, they couldn't maintain the observed brightness. The energy density would be too high. Something else was happening here. Something beyond the realm of stellar physics. Yet the evidence stared back at him from the spectral lines, undeniable and impossible. But 3C273 was only the beginning. Throughout the 1,950 seconds and early 1,960 seconds, radio astronomy had revealed a new universe invisible to optical telescopes. The development of radio astronomy began in earnest after World War II, using surplus military radar equipment and new engineering techniques developed during wartime. Engineers who had spent years developing radar systems for aircraft detection and naval applications turned their expertise toward the cosmos. Radio telescopes could observe the sky regardless of weather, daylight, or atmospheric conditions that plagued optical astronomy. They revealed a cosmos that bore little resemblance to the optically visible universe. While optical telescopes showed a cosmos dominated by stars and galaxies, radio telescopes detected powerful sources of emission that often had no obvious optical counterparts. Some radio sources corresponded to known objects like the Crab Nebula. a supernova remnant in our own galaxy. In 1948, astronomers had identified Cygnus A, one of the brightest radio sources in the sky, with a distant galaxy. But many radio sources remained mysterious, producing strong radio signals without any clear visible counterpart. The new generation of radio surveys cataloged these mysterious objects systematically. The Cambridge University Radio Astronomy Group conducted several systematic surveys of the northern sky. The third Cambridge Catalogue of Radio Sources, published in 1959 and revised in 1962, listed hundreds of radio sources across the northern sky. Each received a catalog number like 3C 273, indicating it was the 273rd object in the third Cambridge Catalogue. Radio astronomers measured positions, flux densities at different frequencies, and spectral indices for these sources, building a comprehensive census of the radio sky. The challenge came in identifying these radio sources with optical counterparts. Radio telescopes of the era had relatively poor angular resolution compared to optical telescopes. A typical radio telescope might localize a source only to within several arc minutes on the sky, a region that could contain multiple faint optical objects. Which one, if any, was the source of the radio emission? The question proved difficult to answer with certainty. Technological advances helped solve this problem. The technique of interferometry, combining signals from multiple radio telescopes separated by large distances, dramatically improved angular resolution. By connecting two or more radio dishes and comparing the signals they received, astronomers could achieve angular resolutions far exceeding what any single dish could provide. By the early 1960 seconds, radio astronomers could pinpoint source positions to within a few arc seconds, good enough to identify specific optical objects with confidence. When astronomers finally located the optical counterparts of these radio sources, many appeared startlingly similar to each other. They looked like faint stars, not fuzzy nebulae or clouds of gas, not resolved galaxies with visible spiral arms or elliptical shapes, just point-like sources indistinguishable from stars except for their unusual colors and, of course, their powerful radio emission. In 1960, astronomer Alan Sandage at the Mount Wilson and Palomar observatories examined photographs of the positions of several radio sources and found these star-like counterparts. He described them as quasi-stellar objects, radio sources that appeared star-like in photographs but clearly weren't normal stars. The name captured their paradoxical nature. They looked like stars, but the combination of properties, the powerful radio emission, the unusual colors, the high luminosities implied by their faintness, suggested something entirely different. Quasi-stellar became the standard terminology, eventually shortened to the more convenient term quasar. Astronomer Hongyi Chu first used the term quasar in print in a May 1964 article in Physics Today. The contraction quickly caught on. Within a few years, quasar had entered the standard astronomical vocabulary, even as the objects themselves remained profoundly mysterious. The mystery deepened as astronomers obtained spectra of more of these objects. Spectroscopy, the technique of spreading an object's light into its component wavelengths, reveals chemical composition, temperature, density, and motion. Every element produces a characteristic pattern of spectral lines, a kind of fingerprint that allows astronomers to identify elements in distant objects. Hydrogen produces lines at specific wavelengths. Helium has its own distinct pattern. Oxygen, carbon, iron. Each element creates recognizable signatures. For normal stars, these spectral patterns are familiar and interpretable. Astronomers had been studying stellar spectra for decades, developing classification schemes based on temperature, composition, and other properties. Star spectra made sense. They followed predictable patterns, but quasar spectra made no sense at first. like 3C 273, they showed emission lines that didn't match any known pattern. In December 1960, Thomas Matthews and Alan Sandage had identified 3C48, another quasi-stellar radio source, obtaining its optical position and taking its spectrum. But that spectrum remained completely baffling for more than 2 years. The emission lines appeared at wavelengths that corresponded to no known element or molecule. Astronomers considered various exotic explanations. Unknown elements, perhaps created in some unusual nuclear process, bizarre physical conditions that might alter atomic transitions, instrumental artifacts in the spectrograph. None of the explanations seemed satisfactory. Jesse Greenstein, a prominent spectroscopist at Caltech, studied the spectrum intensively. He couldn't make sense of it. Other astronomers tried their hand at interpretation. The spectrum stubbornly refused to yield its secrets. It became one of the great puzzles in observational astronomy. Once Schmidt made his breakthrough with 3C 273 inches early, 1963, recognizing the highly redshifted hydrogen lines. 3C48's puzzle solved itself within days. Astronomers re-examined its spectrum with the new understanding that the lines might be familiar atomic transitions shifted to much longer wavelengths. Suddenly, the pattern became clear. The emission lines were magnesium, oxygen, and neon, all highly redshifted. Its redshift of 0.367 placed it even farther than 3C 273, at a distance of roughly 3.5 billion light-years, about 60% farther away than Schmidt's discovery. More quasars followed rapidly. Armed with the knowledge that strong radio sources with star-like optical counterparts might show large redshifts, astronomers obtained spectra of additional objects. Many showed redshifts exceeding 0.1, placing them at distances of 1 billion light-years or more. Some showed redshifts above 1, corresponding to distances where the universe was less than half its current age. By 1965, astronomers had catalogued dozens of quasars. By 1970, the number reached into the hundreds. A profound debate erupted in the astronomical community. The implications of these redshifts seemed too extreme to accept. If these objects truly lay at cosmological distances indicated by their redshifts, they would be radiating with luminosities that exceeded any known object by factors of hundreds or thousands. The energy requirements seemed impossible to satisfy with any known physical process. Some astronomers argued these redshifts couldn't possibly be cosmological. Perhaps quasars were relatively nearby objects, unusual stars, or exotic compact objects in our own galaxy, or ejected from our galaxy, or nearby galaxies at tremendous velocities. Their redshifts would then result from their actual motion through space, Doppler shifts, caused by recession velocity rather than cosmological expansion. This would explain their brightness without requiring impossibly powerful energy sources. A quasar, at a distance of, say, 10 million light-years instead of 2 billion light-years, would need 40,000 times less total luminosity to appear as bright as observed. The ejection hypothesis had some distinguished supporters. Several astronomers suggested that quasars might be objects ejected from the centers of nearby galaxies at relativistic velocities. Perhaps violent explosions in galactic nuclei could accelerate compact objects to tremendous speeds. The ejection would produce the observed redshift through the Doppler effect. The objects would still be unusual, requiring exotic physics to explain their ejection mechanism and their radio emission. But at least their energy output would be within conceivable bounds. Others insisted the redshifts were genuine signatures of cosmic distance, meaning these objects truly possessed luminosities that dwarfed entire galaxies. They pointed to the patterns in quasar properties, the correlations between different observables, the statistical properties of quasar populations. These patterns made more sense if quasars were at cosmological distances. The local hypothesis required special pleading and multiple ad hoc assumptions. The debate raged through the 1,960 seconds, sometimes becoming quite heated. Scientific reputations were staked on one interpretation or another. Conferences featured spirited exchanges between proponents of different views. Papers arguing for local versus cosmological interpretations appeared in rapid succession in the astronomical journals. If quasars were as distant as their redshifts suggested, they would need to generate energies of 10 to the 45th ergs per second, thousands of times the luminosity of the Milky Way galaxy. In the 1,960 seconds, no commonly accepted physical mechanism could account for such prodigious energy output. The numbers seemed too large to be real, too extreme to fit into the known physics of stars and galaxies. Yet gradually, multiple independent lines of evidence confirmed that quasars were indeed at cosmological distances. In 1965, Maarten Schmidt discovered that the number density of quasars increased dramatically at higher redshifts. He found more quasars at larger distances than at smaller distances. Specifically, he showed that quasars were roughly 100 times more common at redshift 2 than at redshift 0.2. This pattern suggested that quasars were far more common in the distant past than in the present. The universe was evolving. Galaxies were changing over cosmic time. This fit naturally with cosmological models of an evolving universe, but made little sense if quasars were local objects randomly distributed in velocity space. If quasars were objects ejected from nearby galaxies, their redshifts would reflect their ejection velocities. There was no reason to expect a systematic pattern where higher velocity, higher redshift objects were more common. The observational results strongly favored the cosmological interpretation. The discovery of gravitational lensing provided even more direct proof. Gravitational lensing occurs when a massive foreground object, like a galaxy or galaxy cluster, bends the light from a more distant background object. Einstein's general theory of relativity predicts this effect. Mass curves spacetime, and light follows the curved spacetime. If the alignment is good, with the foreground mass directly between Earth and the background object's image can split into multiple copies arranged in a ring or arc around the foreground lens. In 1979, astronomers discovered the first gravitationally lensed quasar, an object designated 0957 plus 561. Initial observations showed what appeared to be two distinct quasars with nearly identical spectra and redshifts, separated by only 6 arc seconds on the sky. Detailed study revealed these were actually two images of a single quasar at redshift 1.41, lensed by a massive elliptical galaxy at redshift 0.36. The foreground galaxy split the quasar's image into two visible copies. This observation proved conclusively that the quasar lay far beyond the foreground galaxy, confirming its cosmological distance. The lensing phenomenon itself demonstrated the reality of cosmological expansion and the validity of general relativity on cosmic scales. Over the following decades, astronomers discovered hundreds of additional lensed quasars, each one providing further confirmation of cosmological distances and opportunities to study both the lensing galaxies and the background quasars in detail. Observations of quasar host galaxies provided additional evidence. Beginning in the 1,970 seconds, improved photographic techniques and digital image processing began revealing faint, fuzzy halos around some quasars. These halos had the characteristic appearance of distant galaxies. Advanced image processing techniques could subtract the bright quasar point source, revealing the extended light from surrounding stars. The quasars resided in the hearts of galaxies, not as isolated objects floating in intergalactic space. The host galaxies showed the same redshift as their central quasars. Spectroscopy of the host galaxy light revealed stellar absorption lines at the same redshift as the quasar's emission lines. This confirmed that quasar redshifts were indeed cosmological, representing the expansion of space between Earth and the distant galaxy hosting the quasar. Studies of absorption lines in quasar spectra added another layer of confirmation. When light from a distant quasar passes through intervening clouds of gas, those clouds produce absorption lines superimposed on the quasar's emission spectrum. The absorption lines appear at wavelengths determined by the cloud's redshifts, which are lower than the quasar's redshift since the clouds lie between Earth and the quasar. These intervening absorbers appeared at a range of redshifts between Earth and the quasar, exactly as expected if the quasar lay at great distance, with clouds at various distances along the line of sight. A single quasar spectrum might show dozens of absorption systems at different redshifts, each one representing a gas cloud or galaxy the quasar light passed through on its journey to Earth. The local hypothesis couldn't easily explain this pattern. If quasars were nearby objects, why would their spectra show absorption features from gas clouds, apparently at many different distances? By the early 1970 seconds, the weight of evidence had become overwhelming. The astronomical community reached a consensus. Quasars were indeed at cosmological distances indicated by their redshifts. They were genuinely as luminous as the numbers suggested. They were real cosmic powerhouses, the brightest sustained sources of electromagnetic radiation in the universe. The astronomical community faced a paradigm shift. Accepting quasars as cosmologically distant meant accepting the existence of energy sources more powerful than anything previously imagined. It meant abandoning comfortable assumptions about the limits of cosmic violence. The laws of physics, as understood in the 1960 seconds, were sufficient to explain quasars, but only by invoking conditions more extreme than anyone had considered. The universe, it turned out, could be far more extreme than anyone had suspected. To understand what could produce such impossible luminosity, astronomers had to look to the darkest objects in the cosmos. In 1964, even as the debate about quasar distances continued, two physicists independently proposed a radical solution to the energy problem. Edwin Salpeter at Cornell University and Yakov Zeldovich in the Soviet Union suggested that quasars might be powered by accretion onto supermassive black holes, objects with masses millions or billions of times that of our Sun. The idea seemed almost as fantastic as the quasars themselves. At the time, black holes remained largely theoretical curiosities, solutions to Einstein's equations that most physicists suspected didn't actually exist in nature. The first strong observational evidence for stellar mass black holes wouldn't emerge until the 1970 seconds, with the discovery of Cygnus X1 and other compact X-ray sources. The concept of a black hole millions of times more massive than the Sun lurking at the center of a galaxy seemed like pure science fiction, yet the physics was compelling. Nuclear fusion, the process that powers ordinary stars, converts roughly 0.7% of an object's mass into energy through Einstein's famous equation, E equals mc squared. This conversion efficiency seems impressively high. Our Sun has converted about 0.03% of its mass into energy over its 5 billion year lifetime and will convert a few tenths of a percent in total by the time it exhausts its hydrogen fuel. But this efficiency pales in comparison to gravitational accretion onto a compact object. When matter falls toward a massive body, it converts gravitational potential energy into kinetic energy. For matter falling onto the surface of a normal star, this conversion is modest. But for matter falling toward a neutron star or black hole, the process becomes far more efficient. Consider matter spiraling into a black hole. It doesn't fall straight in. Conservation of angular momentum forces the material into an orbital dance, forming a rotating disk. As the material in this disk spirals gradually inward, friction between adjacent rings of gas converts orbital kinetic energy into heat. The gas heats up and radiates this energy away as electromagnetic radiation. The closer the material gets to the black hole, the deeper it falls into the gravitational potential well and the more energy it releases. Material in the innermost stable circular orbit around a black hole, just a few times the radius of the event horizon, moves at appreciable fractions of the speed of light. The energy available for radiation approaches a significant fraction of the rest mass energy. For a non-rotating black hole, theoretical calculations show that up to 5.7% of the infalling mass can be converted into radiated energy. For a maximally rotating black hole, the efficiency can reach 32%. Accretion onto supermassive black holes represents one of the most efficient energy generation mechanisms in the universe. A supermassive black hole accreting material at even a modest fraction of its theoretical maximum rate could easily outshine billions of stars. The mathematics worked. The energy budget finally made sense. If quasars were powered by black holes with masses of 1 million to 1 billion solar masses, accreting gas at rates of a few tens of solar masses per year, they could sustain the observed luminosities for millions or even billions of years. Here's how the mechanism operates in detail. A supermassive black hole sits at the center of a galaxy, its gravitational field dominating the surrounding region. The black hole's sphere of influence, the region where its gravity dominates over the collective gravity of surrounding stars, typically extends for hundreds or thousands of light years. Within this region, the black hole's gravity determines the motion of gas, dust, and stars. Gas and dust from the galaxy, supplied by stellar mass loss, supernova explosions, or infall from intergalactic space, gradually lose angular momentum through various processes. Gravitational interactions with stars, turbulence in the interstellar medium, and magnetic fields all contribute to removing angular momentum. As gas loses angular momentum, it spirals inward, falling deeper into the black hole's gravitational well. Eventually, the gas forms a vast, rotating disk called an accretion disk. This disk doesn't fall straight into the black hole, at least not immediately. Conservation of angular momentum is a fundamental physical principle. For the material to actually fall into the black hole, it must somehow transfer its angular momentum outward. Friction within the disk provides the mechanism. Adjacent rings of gas in the disk orbit at different speeds. The inner rings, deeper in the gravitational well, orbit faster than the outer rings. This differential rotation creates friction, what physicists call viscous dissipation. The friction transfers angular momentum from the inner disk outward and energy from the outer disk inward. Inner material loses angular momentum and spirals inward. Outer material gains angular momentum and moves outward. Energy dissipated by friction heats the disk. As gas moves deeper into the gravitational well, it accelerates to higher and higher velocities. Particles in the inner regions of the accretion disk can reach 10 or even 20% of the speed of light. At these velocities, collisions and friction between particles become catastrophically energetic. The disk heats up, starting at temperatures of thousands of degrees in the outer regions and climbing to millions of degrees near the innermost stable orbit, the last stable circular orbit before material plunges into the black hole. Matter at temperatures of millions of degrees doesn't glow with the gentle light of a campfire or even the fierce light of the sun's 6,000-degree surface. It radiates across the entire electromagnetic spectrum, from radio waves through visible light to X-rays and gamma rays. The inner regions of the accretion disk shine with such intensity that they can outshine 100 billion stars, all from a region that might be only a few light hours across, smaller than our solar system. The compactness of quasars became evident through their variability. Astronomers noticed that quasar brightness could fluctuate significantly over timescales of days, weeks, or months. Some quasars showed variations on timescales of hours. This variation provided crucial information about their size through a principle called light travel time. Consider a sphere of radius r that suddenly turns on, beginning to emit light. Observers watching from a great distance will see the brightness increase gradually over a time equal to r divided by the speed of light, because light from the far side of the sphere takes longer to reach them than light from the near side. An object cannot vary in brightness coherently faster than light can cross its diameter. If a quasar's brightness changes noticeably in a day, some quasars show variations on timescales of hours, constraining their size to less than the orbit of Neptune. Yet these tiny regions, by cosmic standards, outshine entire galaxies. For comparison, the Milky Way galaxy spans 100,000 light-years, about 300 trillion kilometers. Quasars pack luminosities thousands of times greater into regions billions of times smaller. The energy density approaches incomprehensible levels. Consider TON 618, one of the most luminous quasars known, located at a distance of approximately 4 billion light-years, with a redshift of 2.219. At its center sits a supermassive black hole weighing in at roughly 66 billion solar masses, making it one of the most massive black holes ever detected. This black hole is so massive that its event horizon has a radius of about 1,300 astronomical units, roughly 40 times the distance from our Sun to Neptune. The sphere of gravitationally captured light around this monster extends nearly a light week across. The quasar shines with a luminosity exceeding 4 times 10 to the 40th watts, equivalent to about 140 trillion times the Sun's luminosity, or roughly 4,000 times the luminosity of the entire Milky Way galaxy. All this light emerges from the accretion disk surrounding the black hole, a structure that probably extends outward for light months but emits most intensely from its inner regions. The accretion disk around such a monster would extend for tens of billions of kilometers, glowing at temperatures ranging from thousands of degrees in the outer regions to millions or tens of millions of degrees in the inner disk. The innermost regions, where the disk orbits just outside the innermost stable circular orbit, would shine with such intensity that they would instantly vaporize any material object. The radiation pressure alone would be sufficient to blow apart incoming matter, yet somehow the disk maintains itself, continuously feeding the black hole while simultaneously radiating away enormous quantities of energy. There's a theoretical limit to how fast a black hole can accrete matter, called the Eddington limit, named after British astrophysicist Arthur Eddington, who first worked out the concept. When radiation pressure from the accretion disk becomes strong enough, it can actually push away infalling material, creating a natural throttle on the accretion rate. The Eddington limit depends on the black hole's mass. More massive black holes have higher Eddington limits and can accrete more matter per unit time. For a black hole to maintain its brilliant quasar phase, it must walk a fine line, accreting at or near this Eddington limit, maximizing its energy output without blowing away its fuel supply. Some quasars may actually exceed the Eddington limit temporarily through various mechanisms, a process called super-Eddington accretion. But sustained accretion at rates far above Eddington seems difficult to maintain. But the accretion disk, for all its spectacular power, was only half the story. Many quasars displayed another remarkable phenomenon: jets of material streaming away from the central black hole at speeds approaching the speed of light. In early photographs of 3C 273, even before Schmidt determined its distance, astronomers noticed something peculiar. Extending from the quasar's brilliant core was a luminous jet, stretching across hundreds of thousands of light-years of space. The jet appeared as a narrow, elongated feature in optical images, glowing with its own light. At first, this jet seemed like a minor curiosity compared to the overwhelming mystery of the quasar's central luminosity. As more quasars were discovered and studied in detail, however, jets emerged as a fundamental feature of these objects. Many quasars possess them, and they appeared to channel enormous amounts of energy across distances that spanned significant fractions of their host galaxies and beyond. These weren't gentle flows of gas drifting lazily outward. Measurements revealed that material in these jets traveled at velocities approaching the speed of light, often exceeding 90% of light speed. At such velocities, special relativity's effects become impossible to ignore. Time dilates, lengths contract, masses increase. The jets represented some of the most extreme physical conditions in the universe outside of the surfaces of neutron stars or the regions immediately adjacent to black hole event horizons. But how could accretion disks, which orbit in a plane around the black hole's equator, produce jets that shoot outward perpendicular to that plane along the black hole's rotation axis? The answer involves one of the most powerful mechanisms in astrophysics, proposed by Roger Blandford and Roman Znajek in 1977. A rotating black hole, the equations of general relativity show, possesses rotational energy that can, in principle, be extracted. The black hole's spin drags the surrounding spacetime itself into rotation, a phenomenon called frame dragging, or the Lense-Thirring effect. Near the event horizon, spacetime rotates with the black hole, whether matter wants to or not. Magnetic field lines threading through the accretion disk and anchored in the surrounding plasma get twisted and wound up by this rotating spacetime. As the magnetic fields get twisted, they grow stronger and stronger, creating enormous magnetic pressure. The geometry of these twisted field lines creates a configuration where the magnetic pressure is highest along the rotation axis, perpendicular to the accretion disk. This magnetic field geometry naturally channels material along the rotation axis, where the magnetic pressure is most intense. Particles caught in these magnetic field lines get accelerated to relativistic speeds through a complex magneto-hydrodynamic process that converts magnetic energy into kinetic energy. The exact mechanism by which jets form and accelerate remains an active area of research. Theoretical models and computer simulations suggest multiple processes contribute. The twisting of magnetic field lines by the spinning black hole extracts rotational energy. Magnetic reconnection events, where tangled field lines snap and reconnect in new configurations, can accelerate particles impulsively. MHD waves propagating along the jet can carry energy and momentum from the accretion disk to larger distances. But observations and simulations increasingly confirm the basic picture. Rotating black holes embedded in magnetized accretion disks naturally produce relativistic jets. The jets emerge as narrow beams, typically only a few light years across near the black hole, but extending for hundreds of thousands or even millions of light years into intergalactic space. They maintain their remarkable collimation, their narrow geometry, through a combination of magnetic confinement and interaction with the surrounding medium. The magnetic fields within the jet create an effective magnetic pressure that resists expansion. Meanwhile, the jet interacts with the surrounding gas, whether the interstellar medium of the host galaxy or the more diffuse intergalactic medium beyond. This interaction can help confine the jet and channel its flow. Where jets slam into the intergalactic gas, they create enormous radio lobes, regions where the jet energy thermalizes and produces synchrotron radiation from electrons spiraling in magnetic fields. These radio lobes can extend far beyond the visible galaxy, creating structures spanning millions of light years. The jets deliver energy and momentum from the central black hole to these distant regions, inflating the radio lobes and heating the surrounding gas to high temperatures. The galaxy Centaurus A, located only 13 million light-years away, hosts one of the most spectacular jet systems visible from Earth. Radio observations reveal jets extending over 1 million light-years from the galaxy's center, powered by a supermassive black hole of approximately 55 million solar masses. Measurements using very long baseline interferometry, a technique that combines signals from radio telescopes across Earth to achieve extraordinary angular resolution, show the jet material moving at approximately half the speed of light. The jets from Centaurus A carry away enormous quantities of energy and momentum from the central engine, depositing that energy in the intergalactic medium surrounding the galaxy. The jets appear to pulsate and vary over timescales of years, suggesting the central accretion process is highly dynamic and turbulent. At other times, bright knots of emission appear and move along the jet, suggesting blobs of enhanced emission traveling outward at relativistic speeds. For more distant quasars, the jets can appear even more dramatic due to an effect called relativistic beaming. This effect arises from special relativity. When a jet points nearly directly at Earth, moving at close to the speed of light, several relativistic effects combine to dramatically enhance the observed emission. The light we receive becomes concentrated in the forward direction. The frequency of the light becomes blue-shifted to higher energies. Time appears dilated, making variations appear faster than they actually occur. All these effects combine to make the approaching jet appear extraordinarily bright. Quasars, whose jets happen to point almost directly at us, are called blazars, and they represent some of the most variable and luminous objects in the sky. The quasar 3C 279, located at a distance of about 5 billion light-years, is a well-studied blazar whose jet produces gamma rays, the highest energy form of electromagnetic radiation. Observations suggest the jet in 3C 279 contains both electrons and their antimatter counterparts, positrons, all accelerated to velocities exceeding 0.99 times the speed of light. Blazars can vary dramatically in brightness over timescales of hours or days. Their rapid variability arises partly from the jet emission itself varying, but also from the relativistic beaming effect amplifying these variations. When a bright knot of emission moves along the jet toward Earth at close to light speed, relativistic effects make it appear to brighten and then fade much more rapidly than would be observed if the jet were not pointed toward us. These relativistic jets serve as cosmic particle accelerators, creating some of the highest energy particles in the universe. The mechanisms of particle acceleration in jets remain under study, but observations confirm that jets accelerate particles to extraordinary energies. When astronomers detect ultra-high energy cosmic rays striking Earth's atmosphere, carrying energies that exceed what the largest human-built particle accelerators can achieve by factors of millions, many researchers suspect these particles originated in distant quasar jets or similar astrophysical accelerators. The acceleration mechanisms in these jets can boost particles to energies of 10 to the 20 electron volts or higher, approaching theoretical limits imposed by interactions with the cosmic microwave background. At these extreme energies, particles interact with photons of the cosmic microwave background through a process called the GZK effect, named after physicists Greisen, Zatsepin, and Kuzmin, who predicted it. This interaction limits how far ultra-high energy particles can travel before losing significant energy. The sheer scale of these jets staggers the imagination. A jet extending 1 million light-years means that light itself takes 1 million years to traverse the jet's length. Material ejected from the central black hole today won't reach the end of the jet for 1 million years, even assuming it travels at close to light speed. These structures represent some of the largest coherent phenomena in the universe, evidence that processes occurring at the heart of galaxies can influence regions far beyond the visible galaxy itself, reshaping the intergalactic medium and affecting the evolution of surrounding structures. But these jets weren't just spectacular cosmic phenomena. By the late 20th century, astronomers faced a puzzle in their models of galaxy formation and evolution. According to standard theories developed through the 1970 seconds and 1980 seconds, gas in large galaxies should cool efficiently, falling inward under gravity and forming vast numbers of stars. The cooling process seems straightforward. Hot gas radiates energy. As it radiates, it cools. As it cools, it becomes denser. Denser gas cools even more efficiently. A runaway cooling process should drive gas rapidly toward galaxy centers. The models predicted that massive elliptical galaxies should be much more massive than observations indicated, containing far more stars than astronomers actually saw. The galaxies should have converted much more of their gas into stars over the past billions of years. This became known as the overcooling problem, or the cooling catastrophe. The theory predicted too much star formation, creating galaxies more massive than observed. Something was preventing gas in massive galaxies from cooling and forming stars as efficiently as the models suggested. Some source of energy had to be heating the gas, keeping it too hot to collapse and fragment into stellar nurseries. Supernova explosions from massive stars provide significant energy feedback in smaller galaxies. When massive stars explode, they inject enormous energy into the surrounding gas, heating it and driving winds that can remove gas from the galaxy entirely. But in the most massive systems, galaxies with masses exceeding 1 trillion solar masses, supernova feedback alone couldn't solve the overcooling problem. The energy budget didn't add up. Supernovae provided too little energy compared to the cooling rate of gas in these massive systems. Some additional energy source was needed. Astronomers gradually realized that supermassive black holes provided the missing energy source. When a black hole accretes matter, converting 5 to 30% of the infalling mass into energy, it releases up to 20 to 50 times more energy per unit mass than supernova explosions, which convert roughly 1% of a star's mass into explosive energy. Even a relatively modest accretion rate could pump enormous quantities of energy into a galaxy's interstellar medium. The question was how this energy coupled to the surrounding gas. A black hole at the galaxy center, surrounded by a brilliant but compact accretion disk, might not seem obviously capable of heating gas throughout the galaxy, which extends for hundreds of thousands of light years. The answer involved both the jets and the radiation from the accretion disk itself. When powerful jets plow into the surrounding gas, they create powerful shocks, discontinuities, where the jet material collides with the ambient gas at supersonic speeds. These shocks heat the gas to temperatures of millions or even tens of millions of degrees. The hot gas becomes buoyant, rising away from the galactic center like hot air rising above a radiator. This creates turbulent convection in the galaxy's gas, stirring the cooler gas and preventing it from settling into a disk where it could cool efficiently and form stars. The jets also do mechanical work on the surrounding gas, pushing it aside and inflating enormous bubbles or cavities. These cavities appear as holes in the X-ray emitting gas surrounding massive galaxies and galaxy clusters. The work done in inflating these cavities represents energy delivered from the black hole to the surrounding medium, energy that prevents the gas from cooling and falling back toward the galaxy center. Simultaneously, the intense radiation from the quasar's accretion disk exerts radiation pressure on gas and dust, physically pushing material away from the galaxy's center. Radiation pressure arises because photons carry momentum. When photons are absorbed or scattered by gas and dust, they transfer their momentum to the matter. In the most luminous quasars, where radiation output reaches or exceeds the Eddington limit, radiation pressure becomes a powerful force capable of accelerating gas to high velocities. In the most luminous quasars, radiation pressure alone can drive outflows at velocities exceeding 1,000 kilometers per second. These outflows sweep through the galaxy like cosmic tsunamis, removing the raw material needed for star formation. Gas that might have settled into molecular clouds and eventually formed stars instead gets heated and expelled, either blown out of the galaxy entirely or deposited in a hot halo surrounding the galaxy where it cannot cool efficiently. Observations have confirmed this feedback mechanism in action. Using the Herschel Space Observatory, a space-based infrared telescope that operated from 2009 to 2013, astronomers studied ultra-luminous infrared galaxies, systems undergoing intense starbursts while simultaneously hosting active galactic nuclei. These galaxies represent an important phase in galaxy evolution, when vigorous star formation and black hole growth occur together. The Herschel observations detected molecular outflows traced by absorption lines from the hydroxyl molecule OH. When light from the galaxy's central regions passes through outflowing gas, molecules in that gas absorb light at specific wavelengths, creating absorption features in the spectrum. By measuring the wavelength shift of these absorption features, astronomers could determine the velocity of the outflowing gas. These observations showed winds moving at velocities ranging from 200 to 1,000 kilometers per second, carrying away gas at rates of several hundred solar masses per year. In the most extreme cases, the outflow rates exceeded the star formation rates, meaning the galaxy was expelling gas faster than it was forming stars. At this rate, the galaxy would exhaust its gas supply within a few tens of millions of years, quenching star formation and transforming from a blue, star-forming galaxy to a red, quiescent galaxy. The Q-SOFIDE project, a detailed spectroscopic survey of Type II quasars at relatively low redshifts. They found that 85% of their sample showed gas velocity dispersions significantly larger than the stellar velocity dispersions, indicating active outflows. The study analyzed spectra of 48 quasars at redshifts less than 0.14, measuring both the kinematics of ionized gas and the properties of stellar populations. The study measured star formation rates ranging from essentially 0 up to 92 solar masses per year, averaged over the past 100 million years. While the project found no direct correlation between outflow properties and instantaneous star formation rates, the researchers discovered a positive correlation between the light-weighted ages of stellar populations and black hole mass. This suggests that successive episodes of black hole activity, recurring over hundreds of millions or billions of years, gradually suppress star formation over a galaxy's lifetime. The most direct evidence came from studies of the most distant quasars, systems seen as they appeared when the universe was less than 1 billion years old. When astronomers discovered the quasar J313 1,806 inches 2021, they found something remarkable. This quasar, visible as it appeared just 670 million years after the Big Bang, showed clear spectroscopic signatures of a powerful wind flowing outward at roughly 20% the speed of light. The wind carried enough momentum and energy to potentially blow most of the galaxy's gas into intergalactic space, effectively quenching star formation before the galaxy could build up a substantial stellar population. The quasar's host galaxy was forming stars at a rate of about 200 solar masses per year, a vigorous pace but far below what would be expected without feedback. The winds from the quasar appeared to be limiting star formation even in this very young galaxy. The feedback process works as a two-mode system, a concept developed through theoretical models and confirmed by observations. During the quasar mode, when large amounts of gas flow inward and the black hole accretes rapidly, the intense radiation and high-velocity winds blast through the galaxy, removing gas and suppressing star formation in the inner regions. The quasar mode operates when abundant cold gas is available, typically during galaxy mergers or in the early universe when gas-rich galaxies were common. Later, as the gas supply diminishes and accretion slows, the system enters radio mode. The black hole continues to accrete at a lower rate, below 1% of the Eddington limit, but now powerful jets dominate over radiation. These jets inflate enormous bubbles of hot gas in the surrounding medium, preventing fresh gas from cooling and falling back into the galaxy. The radio mode represents a maintenance phase, preventing gas cooling rather than violently expelling gas. Over billions of years, cycling between these modes, the feedback establishes an equilibrium. The supermassive black hole grows to a mass that is approximately 1/200th the mass of the galaxy's stellar bulge. This remarkably consistent ratio, observed across many galaxies spanning a wide range of masses, suggests a fundamental connection between black hole growth and galaxy evolution. The black hole regulates its own growth by preventing gas from cooling and feeding it, while simultaneously regulating the galaxy's star formation. When the black hole grows too massive relative to the galaxy, its feedback becomes too strong, preventing further gas infall and thereby limiting its own growth. When star formation proceeds too vigorously, it consumes gas that might otherwise feed the black hole. This self-regulation creates the observed correlation between black hole mass and galaxy properties. In the nearby universe, we see the long-term effects of this process. Massive elliptical galaxies, which appear red due to their old stellar populations and lack of young blue stars, typically host supermassive black holes in a quiescent state. These galaxies underwent intense star formation and black hole growth billions of years ago during the peak epoch of quasar activity. The quasar feedback eventually expelled or heated most of their gas, leaving behind red and dead galaxies that can no longer form significant numbers of new stars. Our own Milky Way's supermassive black hole, Sagittarius A star, abbreviated SCIR A star, which weighs approximately 4 million solar masses, provides a local example. Evidence from X-ray observations and studies of molecular clouds near the galactic center suggests that Sagittarius A star experienced an active galactic nucleus phase roughly 8 billion years ago. During that period, the radiation and particle outflows from our galaxy's center would have made regions within several thousand light-years essentially uninhabitable. The intense X-ray and ultraviolet radiation would have stripped away planetary atmospheres over timescales of millions of years and prevented complex life from developing on any worlds in the inner galaxy. The constant bombardment of high-energy particles would have made surface life impossible without substantial shielding. Even Earth, located about 26,000 light-years from the galactic center, would have received elevated doses of radiation during that active phase, though probably not enough to sterilize the surface. Life was already present on Earth 8 billion years ago. Simple, single-celled organisms. The enhanced radiation from the galactic center might have increased mutation rates slightly, but probably didn't pose an existential threat at our distance. Today, Sagittarius A star accretes matter at an extraordinarily low rate, less than 1/10,000th of the Eddington limit. Occasionally, a gas cloud or disrupted star wanders too close, producing a brief flare in X-ray or infrared emission. But most of the time, the black hole remains essentially quiescent. The violent quasar phase that shaped our galaxy billions of years ago is long over. The quasars, in their violence, shaped the galaxies we see today. Without their feedback, the universe would look profoundly different. Massive galaxies would be too massive, overpopulated with stars, their gas having cooled and formed stars too efficiently. The regulated balance between star formation and gas expulsion created by AGN feedback created the diverse population of galaxies we observe, from actively star-forming spirals to quiescent ellipticals. But if quasars were galaxy killers, if their feedback suppressed star formation and expelled gas, why don't we see them killing galaxies today? The answer lies in cosmic evolution. When astronomers survey the universe at different distances and therefore different epochs, a clear pattern emerges. Quasars are rare in the nearby universe. The closest known quasar lies about 600 million light-years away. Within the local universe, within 1 billion light-years of Earth, only a handful of true quasars exist. The vast majority of nearby galaxies host quiescent supermassive black holes. At modest redshifts, corresponding to distances of a few billion light-years and look-back times of a few billion years, quasars become more common. The volume density of quasars increases with redshift. But at redshift z equals 2, corresponding to looking back approximately 10 billion years, when the universe was only about 20% of its current age, or 2.7 billion years old, quasar density reaches a dramatic peak. At this epoch, quasars were hundreds of times more common than in the present-day universe. At still higher redshifts, corresponding to even earlier times, quasar numbers decline again, though they remain far more common than in the present. The decline at very high redshifts probably reflects a combination of factors. Fewer galaxies had formed by that early time, and there hadn't been sufficient time for supermassive black holes to grow to the masses needed to power bright quasars. This distribution tells a story of cosmic evolution. The early universe, despite having had less time for structures to form, produced quasars in far greater numbers than the universe does today. At the peak epoch around redshift 2, the volume density of quasars exceeded current values by factors of hundreds. The universe 10 billion years ago was a much more violent place, with quasars blazing in significant numbers and actively reshaping their host galaxies. Several factors explain this dramatic rise and fall. In the early universe, galaxies contained far more cold gas that hadn't yet been processed into stars. The first few billion years of cosmic history saw vigorous gas accretion onto forming galaxies, with cold gas streaming along filaments of the cosmic web and falling into dark matter halos. This abundant fuel supply could feed supermassive black holes at high rates, triggering bright quasar activity. Additionally, galaxies in the young universe were smaller and more closely packed together. The universe was denser overall. Galaxy mergers and close encounters occurred much more frequently than in the modern universe. When two gas-rich galaxies collided or merged, gravitational torques removed angular momentum from gas, causing vast amounts to lose support and fall toward the newly combined system's center. This triggered intense starbursts and fed the central supermassive black holes, igniting quasar activity. The cosmic web itself played a crucial role. Large-scale structure in the universe consists of galaxies, galaxy groups, and galaxy clusters connected by filaments of dark matter and gas, separated by vast voids. In the early universe, cold gas streams flowed along these filaments, funneling material directly onto forming galaxies. These cold streams provided a continuous supply of fresh fuel to power both star formation and black hole growth. As the universe expanded and aged, these streams became less efficient at delivering cold gas to galaxy centers, reducing the fuel supply for both processes. Over billions of years, multiple processes depleted the fuel supply. Star formation converted gas into stars, locking that material up in stellar form where it couldn't feed black holes except when stars died and returned some fraction of their mass to the interstellar medium. Supernova explosions from massive stars heated and expelled gas from galaxies, particularly smaller galaxies with shallower gravitational potential wells. Most importantly for massive galaxies, the quasars themselves blasted away their own fuel through radiation, pressure, and jets. The accretion disk continuously consumed gas, either swallowing it into the black hole or ejecting it in winds and jets. Once feedback became efficient, quasars essentially cut off their own fuel supply. Without fresh and falling gas to replenish the reservoir, quasars gradually dimmed and eventually shut down. The typical active phase of a bright quasar might last 100 million years, a substantial period but still a mere eye blink compared to the age of the universe. During this phase, the black hole might accrete a few million to a few hundred million solar masses of material, depending on the accretion rate and the duration of the active phase. Once the gas supply ran out, the supermassive black hole entered a quiescent phase, still lurking at the galaxy's center but no longer actively accreting significant amounts of matter. Most supermassive black holes in the present-day universe sit in this dormant state. They're invisible, unless material occasionally falls close enough to be consumed. The black hole at the center of our neighbor galaxy Andromeda, weighing approximately 100 million solar masses, is similarly quiescent. Occasional flares occur when stars wander too close and get tidally disrupted, or when small gas clouds fall inward, but sustained quasar-level activity is absent. Yet quasar activity isn't entirely consigned to cosmic history. When two galaxies collide, tidal forces disrupt gas clouds, causing them to lose angular momentum and fall toward the merged system's center. If one or both galaxies possess substantial gas reserves, not yet exhausted by billions of years of star formation, the merger can ignite AGN activity, creating a quasar that briefly recreates conditions from the universe's youth. Astronomers have discovered several dual quasars, systems where two supermassive black holes, each powering an active galactic nucleus, orbit each other in the aftermath of a galaxy merger. These systems represent a brief phase before the two black holes themselves merge into a single, more massive black hole. One spectacular example, J749 plus 2255, was identified at redshift Z equals 2.17. Initial observations suggested a binary system, but confirmation required detailed follow-up. Observations with the Hubble Space Telescope's high resolution revealed two distinct quasar cores. Spectroscopy with the Keck Observatory showed both had similar redshifts. X-ray observations from the Chandra X-ray Observatory confirmed both were accreting black holes. Radio observations with the Very Large Array detected radio emission from both sources. Together, these observations confirmed this as a genuine binary system, with two quasars separated by only about 10,000 light-years, both active simultaneously, destined to eventually merge into a single, more massive black hole. In roughly 4 to 5 billion years, the Milky Way and Andromeda galaxies will collide and merge. Simulations suggest this merger will drive gas toward the center of the combined system, potentially triggering a period of quasar activity. Both galaxies contain substantial amounts of gas, though much less than galaxies in the early universe. For a cosmologically brief period, perhaps lasting 10 to 100 million years, the merged galaxy might light up as a quasar, visible across billions of light-years of space. During this active phase, any civilization in the merged galaxy would witness spectacular displays in the sky, as the galactic center blazed with quasar luminosity. The night sky would be dominated by a brilliant point of light at the galactic center, outshining the combined light of billions of stars. Depending on the intensity and how directly we face the active nucleus, it might be bright enough to cast shadows at night. Then, as the gas runs out, either consumed by the black hole or expelled by feedback, the merged galaxy, often called Milkomeda in popularizations, will settle into a large elliptical configuration with a quiescent supermassive black hole at its heart, probably weighing around 100 million solar masses. The shift from a quasar-dominated early universe to the quiescent galaxies of today represents one of the major transitions in cosmic history. Understanding this evolution requires studying quasars at the earliest possible times, pushing observational capabilities to their limits. And in those earliest epochs, quasars presented astronomers with a profound puzzle. In 1967, astronomers discovered the quasar 3C9 with a redshift of 2.012. At the time, this represented the most distant object known, with light that had traveled for about 10 billion years to reach Earth. The discovery of quasars at successively higher redshifts continued through the decades. Each new record pushed back our view of the universe's history, revealing conditions in earlier and earlier epochs. By the 1980 seconds, several quasars were known at redshifts exceeding 3, corresponding to times when the universe was less than 2 billion years old. By the 1990 seconds, the most distant known quasars had redshifts around 5. By the early 21st century, the Sloan Digital Sky Survey, a comprehensive mapping of the optical and spectroscopic properties of millions of celestial objects, had discovered quasars, with redshifts exceeding 6, corresponding to times when the universe was less than 1 billion years old. These discoveries posed a serious theoretical challenge. A quasar requires a supermassive black hole, typically with a mass of at least several hundred million to several billion solar masses, to power its enormous luminosity. But how could such massive black holes form so quickly in the early universe? The timeline seemed impossibly tight. Standard black hole formation begins with massive stars. Stars more massive than about 25 solar masses end their lives in core collapse supernovae, leaving behind compact remnants. For the most massive stars, those remnants are black holes, typically with masses ranging from 5 to 100 solar masses, depending on the initial stellar mass and how much mass was lost during the star's evolution. These stellar mass black holes can then grow through 2 mechanisms: accreting gas from their surroundings or merging with other black holes. Both processes take time. Accretion faces a fundamental limit called the Eddington limit. When a black hole accretes matter and radiates energy, that radiation exerts outward pressure that can push away infalling material. For steady accretion to continue, the radiation pressure must not exceed the gravitational attraction pulling material inward. The Eddington limit sets a maximum luminosity, and therefore a maximum accretion rate, for sustained accretion onto a black hole. For a black hole to grow while respecting this limit, its mass increases exponentially with time, with a characteristic doubling timescale of about 45 million years, the Salpeter timescale, named after Edwin Salpeter. Starting from a stellar mass black hole of 100 solar masses, continuous accretion at the Eddington limit for 1 billion years would build a black hole of about 10. That's sufficient to power a modest quasar, but falls short of the billion solar mass black holes observed in some of the most distant quasars. That timeline might work fine for quasars at moderate redshifts, observed a few billion years after the Big Bang. But it fails for the most distant quasars. When astronomers discovered J313 1806 inches 2021, spectroscopic observations measured its redshift at 7.64. Light from this quasar was emitted just 670 million years after the Big Bang, when the universe was a mere 5% of its current age. Yet this quasar hosts a black hole weighing 1.6 billion solar masses. The numbers don't add up using standard formation scenarios. Even if a stellar mass black hole of 100 solar masses formed within the first 100 million years after the Big Bang, leaving 570 million years for growth, continuous accretion at the Eddington limit would produce a black hole of only about 10 million solar masses, far short of the observed one, 6 billion. To reach 1.6 billion solar masses in 570 million years requires either starting with a much more massive seed or accreting at rates substantially exceeding the Eddington limit, or both. Something else must have happened. The most promising solution, though still being tested through observations and refined through theory, involves what's called the direct collapse scenario. Under special conditions in the early universe, vast clouds of cold hydrogen gas, perhaps 100,000 to 1 million solar masses, could have collapsed directly into a black hole without first fragmenting into stars. Normal star formation involves fragmentation. A large gas cloud, cooling and collapsing under its own gravity, doesn't remain as a single entity. Instabilities cause it to fragment into smaller clumps. These clumps fragment further. Eventually, the cloud breaks up into thousands or millions of star-sized pieces, each collapsing to form a star. This fragmentation process prevents any single object from becoming extremely massive during the initial collapse. But under certain conditions, fragmentation can be suppressed. High levels of ultraviolet radiation from the first generation of stars could have provided this suppression. UV radiation can dissociate molecular hydrogen, H2, breaking it into individual hydrogen atoms. Molecular hydrogen is important for cooling because it radiates energy efficiently at low temperatures. Without molecular hydrogen, gas clouds can't cool as efficiently, and they remain at higher temperatures where pressure support is stronger. If a gas cloud remains too hot to fragment, but still gravitationally bound and collapsing, it might collapse as a single entity. Theoretical models suggest that under the right conditions, massive gas clouds in the early universe could have collapsed directly to form black holes of 10,000 to 100,000 solar masses without first forming stars. These direct collapse black holes would provide the massive seeds needed to explain the billion solar mass black holes observed at high redshift. If direct collapse created seed black holes of 10,000 to 100,000 solar masses within the first few 100 million years after the Big Bang, those seeds could then grow through aggressive accretion to reach the observed masses by the time we see the earliest quasars. Some models suggest these early black holes might have accreted at rates exceeding the Eddington limit, a process called super-Eddington accretion. Super-Eddington accretion becomes possible under certain geometric configurations. If the accretion flow is not spherical but happens preferentially along certain directions, radiation can escape preferentially along other directions, allowing matter to continue falling in at high rates without being blown away. Some simulations suggest young black holes in the early universe might have undergone episodes of super-Eddington accretion, rapidly building up mass. The discovery of J313-11806 provided strong support for the direct collapse scenario. Xiaohui Fan, professor of astronomy at the University of Arizona and one of the co-authors of the discovery paper, noted that for this black hole to reach its observed mass of 1.6 billion solar masses by 670 million years after the Big Bang, it would have to have started with a seed black hole of at least 10,000 solar masses. Only direct collapse could plausibly create such massive seeds early enough in cosmic history. Another remarkably distant quasar, ULAS J 1342 plus 0928, discovered in 2017, showed similar characteristics. At redshift 7.54, corresponding to about 690 million years after the Big Bang, this quasar hosts a black hole of approximately 780 million solar masses. Observations with the ALMA telescope array revealed extensive amounts of dust and gas in its host galaxy, indicating rapid enrichment of heavy elements through star formation and supernova explosions. This suggests that the earliest supermassive black holes grew in concert with vigorous star formation in their host galaxies. Both processes contributed to the rapid chemical evolution visible in these ancient systems. Stars formed, lived, and died in supernovae that created and dispersed heavy elements like carbon, oxygen, and iron. Meanwhile, the central black hole accreted gas and grew rapidly. The coevolution of black holes and galaxies, evident in the present-day universe, appears to have been operating even in the universe's first billion years. Even more distant, the quasar designated UHZ1, with a redshift of approximately 10.1, pushes back to roughly 400 to 500 million years after the Big Bang. At such early times, the universe had barely begun forming its first large structures. The first stars probably ignited only 100 to 200 million years after the Big Bang. Yet here, just a few 100 million years later, was a quasar, powered by a supermassive black hole, already actively accreting and shining across cosmic distances. To find these ancient beacons, astronomers developed sophisticated search techniques. The Wide Field Infrared Survey Explorer, or WISE, a space telescope launched in 2009 that surveyed the entire sky in infrared light, provided crucial data. Quasars at high redshift have their optical and ultraviolet light stretched into the infrared by cosmic expansion. A quasar emitting primarily in the ultraviolet, as seen in its own rest frame, appears as an infrared source when observed from Earth if its redshift is sufficiently large. By combining WISE data with ground-based optical and infrared surveys, astronomers could identify candidates that showed the characteristic colors of very distant quasars. These objects appear bright in infrared but faint or absent in optical bands because their light has been redshifted so much that their optical and UV emission now falls in the infrared. Spectroscopic follow-up observations confirmed the candidates' redshifts and distinguished genuine high redshift quasars from other objects that might have similar colors. This required some of the world's largest optical and infrared telescopes. The twin 6.5-meter Magellan telescopes at Las Campanas Observatory in Chile, the 10-meter Keck telescopes on Mauna Kea in Hawaii, the large binocular telescope with its pair of 8.4-meter mirrors in Arizona, and the four 8.2-meter telescopes of the Very Large Telescope in Chile all contributed to discovering and characterizing the most distant quasars. These observations required pushing the telescopes to their limits. High redshift quasars, while luminous in absolute terms, appear faint from Earth due to their enormous distances. Obtaining spectra with sufficient signal-to-noise ratio to measure redshifts accurately and study the quasar's properties required hours of integration time on the largest telescopes. Teams of astronomers competed to find and characterize the most distant objects, each new record providing insights into the early universe. The observations revealed more than just distant light sources. Each quasar spectrum carried detailed information about the conditions along the line of sight between the quasar and Earth. Absorption lines from hydrogen and heavier elements encoded the properties of intervening gas clouds, providing a tomographic map of the universe's structure across billions of light years and billions of years of cosmic time. These absorption line systems revealed the chemical enrichment of the universe, showing how the abundance of heavy elements increased with cosmic time as successive generations of stars lived and died. They revealed the temperature and ionization state of intergalactic gas. They mapped the distribution of matter, showing where gas was concentrated into filaments and where vast voids existed. Most intriguingly, these distant quasars offered windows into one of the universe's most important transitions, a phase called cosmic reionization. In the universe's first 380,000 years, matter consisted of a hot, dense plasma of protons, electrons, and helium nuclei suffused with intense radiation. The universe was opaque to light because free electrons scattered photons efficiently, preventing light from traveling far before being absorbed or scattered. As expansion cooled the universe, eventually the temperature dropped below about 3000 Kelvin, allowing electrons to combine with nuclei to form neutral atoms, mostly hydrogen with about 25% helium by mass. This recombination made the universe transparent to light for the first time. Photons could now travel freely through space without immediately scattering off free electrons. The cosmic microwave background we observe today represents photons that last scattered off electrons at the moment of recombination, now stretched to microwave wavelengths by 13.8 billion years of cosmic expansion. For the next few 100 million years, the universe entered its dark ages. No stars yet existed to produce light. The cosmos consisted of vast clouds of neutral hydrogen gas, slowly collapsing under gravity to form the first structures. This neutral hydrogen efficiently absorbs ultraviolet light at wavelengths shorter than 121.6 nanometers, the Lyman alpha wavelength. The universe was opaque to UV radiation, creating a kind of cosmic fog. Then, between roughly 400 million and 900 million years after the Big Bang, the first stars ignited. These primordial stars, likely far more massive than typical stars today, perhaps 50 to 200 solar masses, burned hot and bright, pouring out intense ultraviolet radiation. This UV light had enough energy to ionize hydrogen atoms, splitting them back into protons and free electrons. Around each star and early galaxy, a bubble of ionized hydrogen formed and expanded. The UV photons from stars could ionize hydrogen atoms within a certain radius. Beyond that radius, the neutral hydrogen fog absorbed the UV light, limiting the bubble's growth. But as more stars formed and more galaxies assembled, these ionization bubbles grew and began to overlap. Eventually, they merged, transforming the universe from a mostly neutral state to a mostly ionized state. This reionization represented a fundamental phase transition. The universe transitioned from an opaque, neutral fog to a transparent, ionized plasma that remains transparent to most wavelengths. Reionization fundamentally altered the universe's properties, affecting how gas could cool and form structures, how light could propagate, and how galaxies could evolve. Quasars serve as powerful probes of this reionization process. When light from a distant quasar passes through clouds of neutral hydrogen along the line of sight, the hydrogen absorbs light at specific wavelengths corresponding to quantum transitions in the hydrogen atom. The strongest absorption comes from the Lyman alpha transition, where an electron jumps from hydrogen's ground state to its first excited state, absorbing a photon at 121.6 nanometers in the atom's rest frame. In 1965, James Gunn and Bruce Peterson, astronomers at Caltech and Columbia respectively, predicted that if significant neutral hydrogen existed between Earth and a high redshift quasar, it would produce complete absorption at all wavelengths, shortward of the quasar's own Lyman alpha emission line. This would create a dark trough in the spectrum called the Gunn-Peterson trough, named in their honor. The prediction was clear, but for decades, no such trough appeared in observed quasars. Quasars at redshifts of 2, 3, 4, and even 5 showed Lyman alpha forest absorption. Many individual absorption lines from discrete clouds of neutral hydrogen, but not the complete absorption predicted by Gunn and Peterson. This indicated the universe was highly ionized, out to substantial distances, with only small pockets of neutral gas remaining. Around 2001, the Sloan Digital Sky Survey began discovering quasars at redshifts around 6 and higher. These quasars finally showed the predicted Gunn-Peterson trough. Their spectra showed strong flux at wavelengths blueward of the quasar's rest frame Lyman alpha wavelength, but complete absorption. A nearly flat black spectrum with zero detected flux, redward of that line. This absorption indicated the presence of significant neutral hydrogen between Earth and the quasar. Direct evidence that reionization was still incomplete or had only recently completed at that epoch. The transition happens remarkably sharply. Quasars at redshift 5.7 show minimal absorption from neutral hydrogen, indicating the universe was highly ionized at that epoch. By redshift 6, the Gunn-Peterson trough is fully developed, indicating substantially more neutral hydrogen. This suggests that reionization completed relatively quickly, perhaps over a period of 100 to 300 million years, between redshifts of about 6 and 9. The quasar ULAS J 1342 plus 0928 at redshift 7.54 probes well into the reionization epoch. Its spectrum shows not just a Gunn-Peterson trough, but significant variations in absorption strength across the trough region. These variations suggest the quasar is seeing through a universe that's still in the process of reionizing, where some regions remain neutral while others have already ionized. The patchy nature of reionization, predicted by theoretical models, appears confirmed by these observations. Did quasars themselves contribute significantly to reionization? The energetics work in principle. A single bright quasar produces enough ultraviolet photons to ionize a substantial volume of space, potentially a sphere tens of millions of light-years across. But quasars appear to have been relatively rare even in the reionization epoch. Current evidence suggests that while quasars contributed to reionization, particularly in their immediate environments creating large ionized bubbles, the majority of ionizing photons came from the far more numerous population of early galaxies and their stars. The James Webb Space Telescope, which began operations in 2022, has dramatically enhanced our ability to study the reionization epoch and the earliest quasars. JWST's infrared sensitivity and angular resolution, combining a 6.5-meter primary mirror with modern infrared detectors cooled to just 7 Kelvin, allow it to detect and characterize galaxies and quasars at redshifts exceeding 10, corresponding to the universe's first 500 million years. Early JWST observations have already discovered numerous galaxies at redshifts of 10 and above, far more than expected based on pre-launch models. These observations suggest that galaxy formation began earlier and proceeded more efficiently than previously thought. Ongoing searches are uncovering quasars at similar or higher redshifts, each one providing a window into black hole formation and growth in the universe's infancy. These observations promise to refine our understanding of how the first supermassive black holes formed, whether through direct collapse, through rapid growth of stellar mass seeds, or through some combination of processes. They'll reveal how these early black holes influenced their environments, whether their feedback regulated star formation even in the universe's first billion years, and how the coevolution of black holes and galaxies began. As observations pushed to earlier times and more distant quasars, astronomers recognized that quasar represented just one manifestation of a broader phenomenon called active galactic nuclei. The term active galactic nucleus encompasses any galaxy whose central region shows luminosity and spectral characteristics that cannot be explained by stellar processes alone. A galaxy's nucleus might be bright simply because it contains many stars densely packed together. But some galactic nuclei are far brighter than can be explained by stars, show spectral features incompatible with stellar populations, and vary on timescales incompatible with stellar processes. These are active galactic nuclei. Quasars represent the most luminous end of the AGN spectrum. But many other types exist, forming what astronomers sometimes informally call the AGN zoo. The zoo contains many species, each with distinct observational characteristics, yet all sharing a common underlying cause. At the center of the AGN zoo lies a unified model, developed over decades of observations and theoretical work. According to this model, all AGN are powered by supermassive black holes accreting matter through an accretion disk. The observed differences between AGN types result primarily from three factors: the black hole's mass, the accretion rate, and our viewing angle. The viewing angle matters because of the geometry of the accretion system. Theoretical models and observations indicate that a dusty torus of gas and dust surrounds the accretion disk. This torus, oriented perpendicular to the jets, which emerge along the black hole's rotation axis, has a substantial thickness, extending from perhaps a few light years to tens of light years from the black hole depending on the system's luminosity. When we view the AGN from directions close to the torus's equatorial plane, the dust obscures our direct view of the accretion disk and the region of fast-moving gas close to the black hole. We see only the outer parts of the AGN structure. When we view from directions more aligned with the jet axis, more face-on relative to the disk, we see the central engine more directly. The dust lies to the sides of our line of sight rather than in front of the bright central regions. Quasars typically refer to the most luminous AGN, where we have a relatively unobscured view of the central engine. They appear as brilliant point sources that often outshine their entire host galaxy. The term quasar is sometimes reserved for objects at high redshift, reflecting the historical origin of the term from radio-loud sources discovered in the 1960 seconds. But usage varies among astronomers. Some use quasar for any highly luminous AGN, while others distinguish quasars from other AGN types based on luminosity thresholds or other properties. Seyfert galaxies, named after Carl Seyfert, who studied them in the 1940 seconds, represent lower luminosity AGN in the relatively nearby universe, typically within a few 100 million light-years. Unlike quasars, where the active nucleus overwhelms the host galaxy's light in many observations, Seyfert galaxies show both a bright active nucleus and the surrounding galaxy structure clearly visible. Seyfert galaxies divide into two types. Seyfert type 1 galaxies show both broad and narrow emission lines in their spectra. The broad lines, with widths corresponding to velocities of thousands of kilometers per second, come from fast-moving gas in the broadline region close to the black hole. The narrow lines, with widths of a few hundred kilometers per second, come from slower gas in the narrow line region farther out. Seyfert Type 2 galaxies show only narrow emission lines. The broad lines are absent or much weaker. According to the unified model, this difference arises from viewing angle. In Type 1, we view the AGN more face-on, seeing the broad line region directly. In Type 2, we view more edge-on, with the dusty torus blocking our view of the broad line region. The narrow line region, being more extended, remains visible from all angles. Radio galaxies are AGN with powerful jets that happen to be oriented more or less perpendicular to our line of sight, rather than pointed toward or away from us. We see them primarily through their radio emission from the jets and the enormous radio lobes the jets inflate in the intergalactic medium. Famous examples include Cygnus A, about 600 million light-years away, whose jets span more than 500,000 light-years and end in brilliant radio lobes. The total radio luminosity of Cygnus A equals about 10 million billion solar luminosities. Though this enormous power is spread over radio wavelengths and extended structures, rather than concentrated in the visible light from a compact source, Hercules A shows even larger jets, extending over 1 million light-years. Blazars represent AGN, whose jets point nearly directly at Earth. The relativistic beaming effect, where emission from material moving toward us at relativistic speeds appears amplified, dramatically enhances the emission we receive from the approaching jet. This makes blazars extremely bright and highly variable. Blazars divide into two subclasses. Flat-spectrum radio quasars, or FSRQs, show broad emission lines in their spectra, similar to typical quasars. BL Lacerti objects, or BL-LACs, named after the prototype object BL Lacerti, show weak or absent emission lines. The difference may relate to the properties of the accretion flow. FSRQs appear to have standard thin accretion disks that produce lots of emission lines, while BL-LACs may have different accretion geometries or lower accretion rates that produce weaker line emission. The unified model elegantly explains this diversity of AGN types without requiring fundamentally different central engines. A Seyfert Type 2 galaxy and a Seyfert Type 1 galaxy might be identical objects viewed from different angles. A quasar and a radio galaxy might differ primarily in our viewing geometry rather than in their intrinsic properties. However, some real physical differences exist beyond viewing angle. The mass of the supermassive black hole affects the luminosity, the size scales, and the spectral properties. More massive black holes have larger spheres of influence, larger accretion disks, larger tori, and can sustain higher accretion rates in absolute terms. They can produce more luminous AGN. The accretion rate itself varies widely among AGN. Some AGN accrete near the Eddington limit, converting matter to energy at maximum efficiency and shining as bright as physically possible for their black hole mass. Others accrete at tiny fractions of the Eddington limit, producing much lower luminosities. Our own Sagittarius A star accretes at less than 1/10,000th of its Eddington limit, making it essentially invisible except for occasional flares. The presence or absence of powerful jets adds another dimension of diversity. Only about 10% of AGN produce strong radio jets, visible at large distances from the nucleus. The remaining 90% are radio quiet, producing weak or no extended radio emission. The mechanism that determines whether a particular supermassive black hole launches powerful jets remains incompletely understood. The black hole's spin likely plays a crucial role. Rapidly spinning black holes can more efficiently extract rotational energy through the Blandford-Znajek mechanism, potentially producing more powerful jets. Slowly spinning or non-spinning black holes may produce weak jets or none at all. The properties of the accretion flow, including its magnetic field structure and geometry, also matter. A thick accretion disk might suppress jet formation, while a thin disk threaded with strong magnetic fields might facilitate it. This unified understanding of AGN, developed over decades of observations across the electromagnetic spectrum, from radio to gamma rays, revealed that essentially all massive galaxies host supermassive black holes at their centers. Whether these black holes currently appear as active galactic nuclei depends on whether they're receiving sufficient fuel to power luminous accretion. In the present-day universe, roughly 10% of galaxies show some level of AGN activity, ranging from brilliant quasars that dominate the high redshift universe to much fainter Seyfert galaxies or low-luminosity AGN whose nuclei glow modestly. The other 90% host quiescent black holes, waiting for a new supply of gas to reignite their activity. The diversity of AGN types, once seen as indicating fundamentally different phenomena, now appears as variations on a single theme. Supermassive black holes accreting matter through disks, launching jets, heating surrounding gas, shaping galaxy evolution. The same underlying physics, seen from different angles and operating at different intensities, produces the rich zoo of phenomena we observe. From this cosmic perspective, profound questions emerge about our place in the universe and the processes that shape the galaxies we inhabit. Consider the habitable zones around active galactic nuclei. Within approximately 3,000 light-years of an actively accreting supermassive black hole, based on our current understanding of radiation effects, the environment would likely prove lethal to complex life as we know it. The intense X-ray and ultraviolet radiation would strip away planetary atmospheres over timescales of millions of years. Even with a protective magnetic field like Earth's, surface life would face constant bombardment by high-energy photons and accelerated particles. The radiation doses would be severe enough to damage DNA and other biological molecules at rates far exceeding what natural repair mechanisms could handle. Mutation rates would skyrocket. Cancer rates would be astronomical if life could survive long enough to develop cancer. For most forms of life we can imagine, especially multicellular organisms with limited radiation tolerance. Our own galaxy's supermassive black hole, Sagittarius A star, experienced its last major period of activity roughly 8 billion years ago. During that epoch, any planets within a few thousand light-years of the galactic center would have been rendered uninhabitable by radiation. Earth, located about 26,000 light-years from the galactic center, was far enough away to avoid the worst effects, though radiation levels would have been elevated compared to the present. The Sun itself wouldn't form for another 3.5 billion years after that AGN phase ended. By the time our solar system coalesced from a collapsing molecular cloud 4.6 billion years ago, Sagittarius A star had been quiescent for billions of years. The galaxy's central black hole had exhausted its fuel supply, shut down its quasar phase, and settled into the quiet state we observe today. This raises a sobering thought. If our galaxy's black hole had remained active, continuously accreting at quasar-level rates for the past 8 billion years. A much larger region around the galactic center would remain permanently inhospitable to life. The galaxy would be bright at its core but relatively sterile, at least in its inner regions. The fact that Sagittarius A star went quiet billions of years ago, having exhausted most of its easily accessible fuel supply, created conditions that eventually allowed life to develop on Earth without being sterilized by radiation from the galactic center. In galaxies hosting currently active quasars, particularly those in the early universe where quasar activity was common, life faces severe challenges. The radiation environment, the disruption of gas clouds by jets and outflows, the general violence of the galactic environment, and the difficulty of maintaining stable planetary systems amid such turbulence would make it difficult for stable planetary systems to form and maintain habitable conditions over the billions of years typically required for complex life to evolve. Yet that same quasar activity played a crucial role in shaping the galaxies where life eventually emerged. Without AGN feedback, massive galaxies would have converted too much of their gas into stars too quickly. They might have become densely packed stellar environments where close encounters and disruptions of planetary systems occurred frequently. The regulated star formation, enabled by quasar feedback, may have created the conditions where stable, long-lived environments could exist, where planets could orbit peacefully around stars without constant disruption. The sheer energy scales involved in quasar phenomena boggle the imagination. The jets can extend for millions of light years, channeling enough energy to heat the entire intergalactic medium. An hour of energy output from the brightest quasars exceeds the total energy the Sun will produce over its entire 10 billion year lifetime. These are energies that dwarf anything in human experience by factors of trillions upon trillions. Human civilization currently uses about 20 terawatts of power, 2 times 10 to the 13th watts. The Sun produces about 4 times 10 to the 26th watts. The brightest quasars produce 4 times 10 to the 40th watts, about 100 trillion times the Sun's output, about 10 billion trillion times human power consumption. Yet, all this emerges from processes governed by the same physical laws that govern everyday experience, extrapolated to extreme conditions. Electromagnetism, governed by Maxwell's equations, the laws of thermodynamics, stating that entropy increases and energy is conserved. These familiar principles, worked out using mathematics and tested in laboratories on Earth, accurately describe the spectacular phenomena we observe in quasars billions of light years away. Einstein's general relativity, worked out using pencil and paper between 1905 and 1915, accurately describes the warping of spacetime around supermassive black holes, the extraction of rotational energy that powers jets, the bending of light that creates gravitational lenses. The theory has been tested repeatedly in laboratories, in observations of binary pulsars, through gravitational wave detections. The same theory that explains minute corrections to GPS satellite clocks explains the workings of billion solar mass black holes. Perhaps most remarkably, every observation of a distant quasar is an archaeological discovery. When we observe a quasar at redshift 7, we're seeing light that left that object 13 billion years ago, when the universe was less than a billion years old. We're not seeing that quasar as it is now, in some absolute sense. We're seeing it as it was then, billions of years in the past. By now, that quasar has almost certainly shut down. Its active phase, lasting perhaps 100 million to a few hundred million years, ended billions of years ago. The supermassive black hole consumed or expelled its fuel supply. The brilliant accretion disk faded. The jets switched off. What remains is a large elliptical galaxy with a dormant black hole at its heart, surrounded by old red stars, no longer forming new stars, no longer blazing across the cosmos. The light from these ancient quasars has traveled across most of the observable universe to reach us. During that journey, space itself expanded, stretching the wavelength of the light and redshifting it into the infrared or even radio wavelengths for the most distant objects. The photons we detect in our telescopes, arriving from quasars at redshift 7 or higher, were emitted in the ultraviolet by the quasar. 13 billion years of cosmic expansion transformed them into infrared photons by the time they reached Earth. Each photon carries information encoded in its wavelength, energy, and arrival time. By collecting millions or billions of photons and analyzing their properties, astronomers can reconstruct conditions in that distant quasar, determine properties of the supermassive black hole powering it, and study the state of the intervening universe the light crossed. Future observations promise to push even farther back toward the very first supermassive black holes. The James Webb Space Telescope will detect quasars at redshifts beyond 10, perhaps even beyond 15, seeing back to within 200 or 300 million years of the Big Bang. Future ground-based, extremely large telescopes, like the 30-meter Extremely Large Telescope being built in Chile with a mirror 39 meters across, will complement JWST's infrared capabilities with high-resolution spectroscopy and precision measurements. These observations will test our theories of how the first supermassive black holes formed, whether direct collapse really occurred, what conditions allowed it, and how common it was. They'll reveal the conditions in the universe during its first few 100 million years, when the first stars were forming, the first galaxies assembling, and the first black holes growing. They'll show us the universe in its infancy, wild and violent, very different from the mature cosmos we see around us today. And so we return to where we began, that Tuesday morning in March 1963, when Maarten Schmidt realized that a faint point of light in photographs represented something unprecedented in human knowledge, a discovery that opened entirely new vistas in our understanding of the cosmos. In the 6 decades since that discovery, we've learned that quasars are supermassive black holes, millions to billions of times the sun's mass, gorging on vast quantities of matter flowing through accretion disks. We've learned that the accretion process converts 5 to 30% of infalling mass into pure radiated energy, making quasars the most efficient engines of sustained power in the universe, exceeding even nuclear fusion by factors of 10 to 40. We've learned that powerful jets, launched through complex magnetohydrodynamic processes involving the twisting of magnetic field lines by rotating black holes, carry energy and matter across distances exceeding the spans of galaxies, creating some of the largest coherent structures in the universe. We've measured these jets carrying material at velocities exceeding 90% of light speed, approaching the absolute speed limit imposed by special relativity. We've discovered that quasars once dominated the universe, reaching peak numbers when the cosmos was only 2 billion years old, 10 billion years ago. We've learned that their violence, their radiation, and their jets shaped galaxy evolution by heating and expelling gas that would otherwise form stars, creating the populations of red, quiescent galaxies we see in the present universe. We've found evidence that every massive galaxy hosts a supermassive black hole, most now quiescent, their active phases long since ended. We've measured the correlation between black hole mass and galaxy properties, finding that black holes consistently weigh about 1/200th the mass of their galaxy's stellar bulge, evidence of coevolution between black holes and galaxies over cosmic time. We've pushed observations to the universe's first billion years, finding supermassive black holes already in place, already actively accreting, challenging our theories of how such massive objects could form so quickly. These observations suggest new formation mechanisms, direct collapse of massive gas clouds rather than bottom-up growth from stellar mass seeds. We've used quasars as probes of cosmic history, studying the reionization of the universe, watching the transition from neutral hydrogen fog to ionized transparency. We've mapped the distribution of matter across billions of light years, seeing how gas clumps into filaments and how voids empty over cosmic time. The term brightest killers captures both essential aspects of quasar nature. They are indeed the brightest sustained sources in the universe, more luminous than anything else we observe over cosmological timescales. A single quasar outshines 100 billion stars. The most luminous quasars exceed the brightness of entire galaxy clusters, and they are killers, though perhaps the term judges them harshly. Their feedback mechanisms suppress star formation, removing the raw material that galaxies need to build new generations of stars. Their jets heat gas throughout galaxies and beyond, preventing cooling and collapse. Their radiation strips away gas, sometimes expelling it from galaxies entirely. Yet, killers misses the constructive role quasars played. They are architects as much as destroyers, perhaps more so. They shaped the galaxies we see, regulated their growth, prevented them from consuming all their gas too rapidly, and created the conditions where galaxies like our Milky Way could evolve in relative stability over billions of years. The violence of the quasar epoch, billions of years ago, established the structures and conditions within which life eventually emerged. In the modern universe, most quasars have fallen silent. The abundant gas supplies of the early universe have been exhausted, converted into stars locked in galaxies, or expelled into intergalactic space where it drifts at temperatures too high to easily fall back. The nearest known quasar lies 600 million light-years away. Most galaxies, including our own, host dormant supermassive black holes that rarely accrete significant amounts of matter. Occasionally, galaxy mergers temporarily resurrect quasar activity. When the Milky Way and Andromeda collide in 4 to 5 billion years, the merger may funnel gas toward the combined system's center, potentially igniting a brief quasar phase. For perhaps 100 million years, the merged galaxy might blaze across the cosmos, visible to observers billions of light-years away, briefly recreating conditions that were common 10 billion years ago. Then the fuel will run out again, and the quasar will fade, leaving behind a large elliptical galaxy with a quiescent supermassive black hole at its heart. The quasars taught us that the universe can be far more extreme than we imagined. They revealed objects whose luminosities exceed entire galaxies, whose jets span millions of light-years, whose central engines convert mass to energy with an efficiency that makes nuclear fusion look wasteful by comparison. They showed us that supermassive black holes, millions and billions of times more massive than our Sun, lurk at the hearts of galaxies. Every observation of these distant beacons carries a message from the universe's youth, from epochs when galaxies were smaller, closer together, richer in gas, and more violently active. The light that reaches our telescopes began its journey billions of years ago, in a cosmos that looked profoundly different from today. Galaxies were more irregular, mergers more common, star formation more vigorous, quasars more numerous. Their combined light contributed significantly to the total luminosity of the young universe. That light traveled across expanding space, carried along by the cosmic expansion, stretched and redshifted, traversing billions of light-years and billions of years, finally arriving at Earth to be captured by our telescopes and analyzed by our instruments. Each photon carries information encoded in its wavelength and intensity, telling us about the conditions in that distant quasar billions of years ago, about the properties of the supermassive black hole powering it, about the state of the intervening universe through which it passed. If you found wonder in this journey through cosmic history, through the story of the brightest and most powerful sustained sources of energy in the universe, consider subscribing to explore more of the universe's magnificent mysteries together. The quasars are quiet now, at least in our cosmic neighborhood. The violent epochs that marked the universe's youth have passed. The supermassive black holes remain, patient and dark at galactic centers, occasionally stirring when new fuel arrives but mostly dormant, their spectacular phases long finished. Their legacy surrounds us in the structure of galaxies, the distribution of matter, the chemical enrichment of the cosmos, and ultimately, in the existence of stable environments where life could emerge and contemplate the universe. The light from those ancient quasars still finds us, having journeyed for billions of years across expanding space. It whispers of a universe that was younger, wilder, more violent, and more spectacular. A universe being shaped by forces that defy easy comprehension, by black holes weighing billions of suns, consuming the mass of several Earths every day, and transforming it into light that outshone 100 billion stars. In understanding these distant beacons, we understand a little more about where we came from, how the universe evolved from its fiery beginning into the rich cosmos we inhabit, and what forces shaped the galaxies within which stars like our sun could form, planets like Earth could coalesce, and life could eventually emerge to look back across billions of years and witness the universe that was. The quasars blazed, they shaped galaxies, they killed star formation in their hosts while creating the conditions for other galaxies to thrive. They seeded the intergalactic medium with energy and metals. They regulated the growth of structure across cosmic scales. And now their light reaches us. Messages from cosmic childhood, evidence of an epoch of violence and transformation, reminding us that the universe is stranger, more dynamic, and more magnificent than we could have dreamed before Schmidt decoded those spectral lines in 1963.